This is topic 27, Group 2 of A levels chemistry. Now, what are the elements of Group 2? Beryllium, magnesium, calcium, strontium, barium, and radium. Now, you have studied in AS level chemistry the reactions with oxygen and the flame colors and the reactions with water. But for A levels chemistry, you only need to be able to answer three questions about Group 2. And what are those questions? How does the thermal stability of group 2 carbonates nitrates vary down the group? The answer is same for both carbonates and nitrates. How does the solubility of group 2 hydroxides vary down the group? And how does the solubility of group 2 sulfates vary down the group? Now let's try to answer question number 1 first. Now we know that both group 2 carbonates and group 2 nitrates decompose at a certain higher temperature. Okay, carbonates decompose into oxide and carbon dioxide, and nitrates decompose into oxide, nitrogen dioxide, which is a toxic brown gas, and oxygen. Both of these are decomposition reactions and they occur at a high temperature. Now, it is a fact that down the group, the temperature at which decomposition occurs increases, which means the thermal stability increases. But that is not enough of an answer. We need to explain why. Down the group, the radius of cation increases, and thus successive cation causes less depolarization of anion, so ionic compound requires more temperature to decompose, and hence we say it becomes more thermally stable. Radius of cation increases because the number of shells increased, okay? And thus successive cation causes less depolarization of electron cloud on anion. Anion here is the carbonate ion or the nitrate ion. And why it causes less depolarization? Because when the radius increases, the charged density decreases, and thus it causes less depolarization of anion. So when it causes less depolarization of anion, compound becomes less reactive, okay, and it requires harsher conditions to decompose, and hence we say it becomes more thermally stable. We have answered question number 1. Now let's go to question number 2 and 3. In order to answer question number 2 and 3, we first need to know what enthalpy change of solution is, okay. Enthalpy change of solution is basically the energy or enthalpy change when 1 mole of solute is dissolved in the solvent until no further enthalpy change occurs to form an infinitely dilute solution. And obviously, it is different for every solute. Now, we also need to be familiar with this Hess cycle to answer question number 2 and question number 3. Okay, here we see that this is delta H solution where the solid ionic compound is becoming aqueous cation and anion. It is basically dissolving, right? And here we see lattice energy where the gaseous cation and anion have become the solid ionic compound. It is always negative, okay? And here we see the gaseous cation and anion are forming the aqueous cation and anion, okay? This is delta H hydration. We are basically hydrating the ions and it's also always negative. Now delta H solution can be both positive and both negative. When it is positive, delta H solution is more endothermic. So enthalpically dissolving or forming a solution is less likely to occur. But when it is more negative, delta H solution is more exothermic and thus more likely to occur. So the compound is more likely to dissolve. Delta H lattice energy, we have seen that it is always negative. Okay, let's give it a value of minus x, right? Delta hydration, it is also always negative. Let's give it a value of minus y. Now from ES level chemistry, you should be able to form this equation. Delta H solution is equal to minus delta H lat plus delta H hydration. Why? Because in order to do the same reaction of solid ionic compound to aqueous cation and anion, we just need to reverse this and go from here to here, right? Because we reversed this one, lattice energy, we will have to add a negative sign here. So this becomes minus x plus minus y. So x minus y. Basically, the magnitude of lattice energy minus magnitude of hydration energy. Okay, now down the group, the magnitude of both lattice energy and hydration energy of cation decreases. Okay, it's just a fact, right? But in case of group 2 hydroxides and in case of group 2 sulfates, the situation is different. In case of group 2 hydroxides, the magnitude of lattice energy decreases more than the magnitude of hydration energy. And in case of group 2 sulfates, the magnitude of hydration energy decreases more. So, when you plug in the values, you will notice that the enthalpy change of solution becomes more negative, and here the enthalpy change of solution becomes more positive. So when the enthalpy change of solution becomes more negative, it becomes more exothermic and thus enthalpically more likely to occur. So compound becomes more soluble. Thus group 2 hydroxides become more soluble down the group, and group 2 sulfates become less soluble down the group. That's all.